Welcome to Lecture 16. This is the final content lecture for Exam 3 material. There will be one more lecture. It will be located in the Exam 3 materials box, and it is a practice sheet of problems that are located at the end of the Exam 3 notes. And I will go through writing some equations, doing more stoichiometry problems, just reviewing everything about this material. So, you're prepared for your Exam 3. Just another whole set of examples. All right, let's go ahead and get started. On the very end, there's not a lot to talk about here. We just need to do some practice, really. The first thing we're going to talk about is dilution. Often you need to dilute up a solution because in the lab, for instance, they don't keep all the different molarities of solutions that you might need. So we often make up more concentrated solutions and then dilute them. So let me conceptually talk to you about what I'm talking about. So if I have a concentrated solution, and we talked about this last time, so I have lots of particles dissolved. All right, so this is the concentrated one. And I want to make up a more dilute solution, so the molarity will be lower. Okay? So let's say that this one is 1 molar. And I want to make up a 0.1 molar. Well, what I'm conceptually doing is I am taking a volume, a portion of this solution, and I am transferring it into some water. So that now I have just a few particles corresponding to this and this. So molarity times volume equals the moles that I am going to transfer into the water. So the moles that I transferred to this are the same. I just need to get a new molarity. So for instance, whatever moles I took out corresponding to this little, amount here, usually done with a volumetric pipette. I'm going to start emphasizing those pieces of equipment because the 131 instructors like to ask about them. And you transfer it into some water. Well, the moles that I transferred is equal to the molarity of this original solution times the volume. Well, the moles I put in here is the same. So I'm going to do molarity times volume again for the dilute side. And this was the concentrated side. And I know my volume because I know how much water I put in here. I just need to calculate the new molarity. Or there, you can know 3 of these things and you're always calculating the 4th. So the equation is right here. And you can also think of it as molarity of the concentrated times volume of the concentrated equals molarity of the dilute times the volume of the dilute. Okay? So let's work one problem here in the notes, and then we'll do quite a couple more in the practice at the end. And then we've got one more thing to talk about, and it's just combining the idea of molarity with stoichiometry, and that finishes us up for Exam 3 content. All right, so here's our little example. For example, how much 6 molar HCl is needed to make 250 molar 1 molar HCl? So what I have here is the molarity 1. This is my molarity 2. And this volume goes with the molarity 2. So this is the volume 2. So this is a common way to ask this question. So I am looking for volume 1. I need to know how much of that concentrated stuff do I need to transfer in order to make up this new solution. All right, so we're going to set that equal to each other. All right. Now, you don't have to put your volumes in liters. You can actually leave it in milliliters. Why don't we work that out together and show you that because they're this, they appear on the same, on both sides of the equation. So let's do it without transferring it to liters, okay? So let's take the molarity of the first is 6 molar times the volume, which is what I'm looking for, equals 1 molar times 250. Now your answer will be in milliliters, which is often what you want when you're in the lab because you want to use a piece of equipment that is not measured in liters. So if I take 1 times 250, so 250 divided by 6, and I end up with 41.67 milliliters. So I need to take 41.67 milliliters out of, there we go, right there, of the 6 molar in order to make up that new solution. So this little equation here is very, very handy, okay? And we'll practice it some more as soon as I talk about solution stoichiometry. And it's just applying the mole chart with our molarity to stoichiometry problems. All right, so we're going to work through an example and then we'll get started on that practice. I'm going to scroll. All right, so as indicated in the chart that we drew in our previous lecture, molarity can be used to get to moles, and if moles are involved, we are back to stoichiometry. Most chemistry is done using solutions, so this is the type of stoichiometry problem that is more common in terms of practical use. Therefore, most stoichiometry involving chemical reactions involves concentrations of solutions. There's no difference. It's just how you're getting to moles, okay? So here's our example. Of course, we start off, as always, with a balanced chemical equation. And our second step is, if you're not in moles, get there. So that's what we're going to do. So here's our balanced chemical equation right here. Okay. Determine the volume of 0.225 molar KOH. So that has been put under the KOH with the question mark. And then the 45 milliliters and the 0.225 molar is under the sulfuric acid. All right, get into moles. Well, the nice thing about this is you don't need the periodic table. All you're going to do is take the molarity times that volume. So let me remind you, it is 0.22, you rewrite the big M in order to get started, okay? So 0.225 moles per liter, and then this does need to be transferred to liters. We do this so often, so it'd be great if you could get used to doing it just by moving the decimal point. That is 0.045 liters. So I'll do it with the conversion. 45 milliliters times 1 liter divided by 1,000. When I divide by 1,000, I am moving the decimal place 3 spots that way. So that's 0.045 liters. We just go back and forth between liters and milliliters so much. All right. When I multiply those two, I will get these moles right here. Okay. 0.225 times 0.045. So those are the moles that I'm going to put right here. So now I'm in moles. Much easier than grabbing the periodic table and adding up molar masses. Then I move because I am now in moles. So that's what they're doing right here. So 1.02 times 10 to the minus 2, right? That's the moles I had of the H2SO4 times 2 over 1 to get the 2.03 times 10 to the minus 2 of the KOH. So I'm going to work that out, writing it over here. It's in the notes, of course. So I end up with 2.03 times 10 to the minus 2 moles of KOH. And I want to know volume. Well, it has a molarity as well. And if I want to know volume, I'm going to rewrite that molarity, rewrite the big M, but I'm going to flip it over because I need liters and I need those moles to be canceled. So 1 liter has 0.225 moles. Okay, so the moles cancel. So I'm taking these moles and dividing by 0.225 to get the final answer. We'll just do it right here before I scroll. And the final answer should be 9.02 times 10 to the minus 2. I'm going to multiply that times 1,000 to put it in milliliters. And I end up with 90.2 milliliters. So it was 0.0902, and that's probably way too many significant figures. No, actually it's 3. Well, I had 2 with the 45 milliliters. So I guess it should be 0.09 liters, but that comes out to be 90 milliliters. So it takes 90 milliliters of the base to neutralize the acid. All right, scrolling, and we should have the same answer as what is in the notes. Hope we do. And there we go. And then here we are at practice, because really we have not, except for the new equation M1 V1 equals M2 V2, we haven't really introduced anything new other than that. Stoichiometry, we know the steps, and we've already practiced how to go between molarity and moles, so we're just putting those two things together. All right, so this practice is going to involve those two things plus a couple of more things that we just need to reinforce here at the end of the exam 3 material. All right, in this first problem, I am reinforcing something that we have talked about, and that is the stoichiometry that is involved when you dissolve particles. So this time we're going to attach a molarity to it. I'm going to do the first one up here, the potassium nitrate. So if I take potassium nitrate and break it up into its ions. So I'm going to write KNO3 is aqueous, and I'm going to break it up into its ions like I would do if I were doing an ionic equation. Okay, of course both of these are aqueous as well. So molarities can be, when you're talking about this kind of thing where things are dissolved, you can take the molarity of the thing before you break it up, and because one of these makes one potassium and one nitrate, they also have the same molarity because of the stoichiometry. So it's like you're doing 1 over 1, okay? And that's perfectly okay to do it this way. Now if you had a solid and you had, you couldn't do that, but you're just talking about taking something that's dissolved and its concentration, and you can extend the concentration to the particles that come out of that dissolving by the stoichiometry. So we did it conceptually before, but now I wanted to attach a molarity to it. This idea comes up all the time in chemistry. In fact, when you get to 132 and you're doing equilibrium, this idea comes up quite a bit as well. Okay, magnesium chloride. We'll do that one down here. Magnesium chloride, if I break it up into its ions, it's 1 magnesium ion and 2 chlorines. Well, if this was 0.1 molar, then the magnesium is 0.1 molar, but the chlorine, because you make 2 of them, is 0.2 molar. So I take 0.1 moles per liter of a compound, and I end up generating 3 particles. I have more particles than I started with. All right, and then the last one, sodium acetate. And if it's 0.1 molar, then when I break it up into its ions, the sodium ion is also 0.1 molar, and the acetate ion is also 0.1 molar because there are 1s in front. Okay, so stoichiometry of dissolving, breaking up compounds. I'm going to scroll. All right, number 2 looks like a dilution question. So you're going to take, so let's dissect it. We have 500 milliliters, so these two pieces go together. That looks like doesn't really matter what side you put them on as long as you keep the right things together. And then 15 molar, that's your concentrated, and they want to know, describe how you would make, so we need to know a volume. That's what we don't know. We don't know the volume of this concentrated solution that I need to make this dilute solution. I'll kind of talk you through the process as we do the problem. So the way I would set up the math is I would say, okay, 15 molar times the volume equals 0.2 molar times the 500 milliliters. All right, so you would take a volumetric pipette, which looks something like this. It's really long. It could be just one. It could be just really long and skinny. Okay, or some of them have like a little bulge in the middle. If it's a, if you're doing like 10 milliliters or so. Anyway, you use a volumetric pipette to get that volume, but we haven't calculated what it is yet. So plug it in the math. 0.2 times 500 divided by 15. So 0.2 times 500 divided by 15. And my answer is going to be in milliliters. And I get 6.67 milliliters. Since this volume was in milliliters, then this volume will also be in milliliters. 6.67 milliliters. So what you would do is you would take a flask, a volumetric flask, and you would, this is the most correct way, and you would take the 6.767 milliliters and you would put it into the volumetric flask with your volumetric pipette, and you would put some of the water, here's your 500 milliliter mark, you'd put some water in there, make sure it dissolves, but usually if you're just diluting, that's not a problem, and then you add water until you get up to this mark. So that's how you would do it, but this is how you would set up the math. How much of a 5 molar sucrose solution, so here's another dilution question. Why don't you stop the video and give this one a try, and then come back. Looks like this 85 milliliters goes with this, okay? So 85 milliliters times 0.04 molar equals 5 molar, and I need to know the volume of that, all right? So 85 times 0.04 divided by 5. And I get 0.68. Going from 5 molar to 0.04 molar is a big change in concentration. 0.68 milliliters is a tough volume to measure. You'd have to have a 1 milliliter volumetric pipette. Okay? So molarity 1, volume 1 equals molarity 2, volume 2. Very, very handy equation. Okay, moving on to, looks like number 4 is just like number 1. So if I have magnesium hydroxide and I break it up into its ions, a strong electrolyte, so it breaks up completely into magnesium ions and hydroxide ions. Okay, the 2 comes in front, all right, as we learned in our doing our ionic equations. So if this is 0.7 molar, then magnesium is 0.7, and hydroxide is twice that. So it's like I'm going times 2 over 1, so this would be 1.4 molar. This is 0.7, and this is 1.4. Okay. Number 5 is very similar. Okay. They want to know what is the concentration of chlorine. So when they ask determine the concentration, they are asking for molarity. That's what they want to know. So we can write the equations. Break this up, so it would be sodium and chlorine. So everything's 1 to 1. So if I started off with 0.2, then each of these is 0.2. So the answer for the chlorine is 0.2 molar for A. Copper chloride, on the other hand, if I start off with 0.2 molar copper chloride, I end up with 2 chlorines and a copper. So if this was 0.2, then this is 0.4, because it's like times 2 over 1. All right? Aluminum chloride, when it breaks up, you get an aluminum and 3 chlorines. So if this first is 0.2, the aluminum is 0.2, but the chlorine is 0.6 because I'm going times 3 over the 1 that would be in front of this. Okay? So the answer to C is 0.6. All right. The 6 and 7 are, and I think I have an 8 now, are stoichiometry. And that will wrap us up. This is going to be a short lecture to finish us off. Again, I've tried to make the lectures shorter in exam 3 because I'm trying to give you enough time to do the practice. You need to master the concepts. So here's our balanced chemical equation. So let's write the information in the problem as we read it. What is the molarity of the zinc chloride? So question mark molarity that forms when 15 grams of zinc, and it's a solid, completely reacts with the copper chloride. Assume a final volume of 175 milliliters. So that's going to be important here. Now this is a solid, so there's no molarity. So we've written our equation, we've put the stuff in the appropriate places, the information. Now if you're not in moles, get there. So that's what we have to do here. All right. I can't solve this question because what I am lacking is moles. I have the volume, but I need to get that from here. All right. So we do need the periodic table for this. And zinc is 65.38 is a molar mass. So 15 grams times 1 mole is 65.38 grams. So divide that mass by the molar mass to get into moles. And I get 0.229 moles. Okay. Moving to the question, looks like it's a 1-to-1. Is my equation balanced? Yes. Okay. So 0.229 moles. And to get molarity, I am going to take those moles and I am going to divide by the volume in liters. Okay, 175 milliliters times 1 liter is 1,000 milliliters. Moving the decimal 3 places in this direction, 0.175 liters. 1.31 molar. Big M. All right. I think solution stoichiometry is a little hard. It seems harder for students, but to me it's easier once you master the idea of molarity. It's just a new concept, but if you keep it straight with the units, it's not hard. I like it because I don't have to add up all those molar masses. It's easier. Okay, 7 is a multi-part question, so let's look and see. So I'm given a balanced chemical equation. What type of reaction is this? Looks like a double replacement to me. Acid-base double replacement. Okay. Or double displacement, same thing. Okay. An acid-base neutralization is another way to categorize it, but that's what it is. Now this whole word neutralization is actually kind of an unfortunate term. What it really means is that when the reaction is completed, the moles of the acid is equal to the moles of the base. But it does not mean we're at necessarily at a neutral pH. So in some ways it's an unfortunate term. All right, so what's my question? How many liters of 0.1 molar, how many liters, so what volume, 0.1 molar, would be required to, it looks like very similar to the previous question, All right. So not moles get there, and I will need to add up some molar masses here. Calcium is 40, 40.1, so I'm going to do it right up here. 40.1 plus 2 oxygens, 32, plus 2 hydrogens. Okay. And I get 74.12 as my molar mass, grams per mole, of course. So take your 5 grams and divide by the 74.12, and you end up with 6.75 times 10 to the minus 2 moles. Right over here. 6.75 times 10 to the minus 2 moles. And then I'm going to move, now that I'm in moles, using the coefficients, times 2 over the 1, so times 2, and I end up with 0.135 moles, but I'm just leaving my calculator alone because that number is still there. And in order to get a volume, I'm going to rewrite the molarity and flip it over. 1 liter has 0.1 moles. So I'm going to take that 0.135 and divide by 0.1, and I will end up with, my moles cancel, 1.35 liters as my answer for B. Okay. Now what I'd like to do for C is, first of all, give myself more room, but I want to write it underneath the equation. So I'm going to erase. So pause if you need to write any of that down. Okay, and so let me erase all of this. I'm going to leave that molar mass up there because I might need it again. All right, and let me give myself just a little more room. That was kind of cramped. Okay, so if we combine 15 grams of calcium hydroxide with 75 milliliters of 75 milliliters of 0.5 molar HCl. What is the limiting reactant? Reagent's another word for reactant. So what do I have to do in order to determine that? I have to put them both into moles. So pause and give that a try. So this one I have to use, oh, what happened to my molar mass? I guess I lost it. Oh, I don't know if I remember it. So 40.1 plus 32 plus 2.02. I think it's 74.12, but I'm going to double check. So 74.12, yes. Because I need that to get this one into moles. So 15 divided by the 74.12, 0.202 moles. All right. This one, I'm going to use the molarity and the volume, rewrite the big M first, 0.5 moles per liter. I want moles, so that's why I'm leaving it as is, times, I have to convert the 75 milliliters to liters, 0.075 liters. And I end up with 3.0375 moles. Okay, so I think it's obvious which one is the limiting reactant before I even divide by the coefficients, because that will be divided by 1, the 0.202 divided by 1 versus 0.0375 divided by 2. The HCl is a limiting reactant. This will be an even, the 0.0375 will be an even smaller number. You know that I don't like to write that number down because I don't use that number, it just tells me which one is limiting. All right, so this is my limiting reactant. Okay. And then, of course, now that we've found our limiting reactant, D asks how many grams of calcium chloride would be formed. So I just want to erase this little bit right here so that I can use that space for the calcium chloride. So I'm going to move from my limiting reactant to the calcium chloride. So the question is grams. I'm in moles, so times, I got a 1 in front of the calcium chloride, so times 1/2 will be my number of moles, divided by 2. So I already had that 0.0375 in the calculator. So I make 1.88 times 10 to the minus 2 moles of the calcium chloride. Now to get it into grams, I do need the periodic table, adding up the molar masses. I know that 2 chlorines adds up to 70.9. So 40.1 plus 70.9. And I get 111 grams per mole. So take those moles times 111 grams per mole so that they cancel. And I get 2.09 grams as my answer for D. Now, I believe I remember that E, which I can't see at the moment, asks how much of the excess is left over, your favorite. So I'm going to have to scroll to make sure of that. So what I need to remember are my molar amounts of, now I can get the writing back, but it'll be all skewed. Okay, so I'm going to write it down on a piece of paper. Okay, just to make sure I don't lose it. Yep, how many grams of the excess will be left over? So let's come back. Let's put in the amounts that I wrote down. So I had 0.202 moles of the calcium hydroxide, and I had 0.0375 moles of the HCl. Go back to the limiting reaction. You have to figure everything, in this reaction from the limiting reactant, and move to the excess times 1/2. So 0.0375 divided by 2, and this is how much you use. I use 0.0188. Okay? Moles. Subtract it from the original. And I end up with 0.183 moles left over. Just double checking. Nope, something's not right. I'll do my calculation again. Okay. .183. Yes, okay, we're good. All right, so needed that molar mass again. I believe it was 74.12. I am going to double check that really quick. All the calcium hydroxide. See how important it is to write it above? Yes. All right, so times, if I want to get it back into grams, and that's usually what they're asking for, times the 74.12 grams per mole. The moles cancel, and that's how many grams of my calcium hydroxide are left over. Now you could have taken the 0.0188, converted it to grams, and then subtracted it from the original grams of the calcium hydroxide. You're doing the same number of conversions, no matter which way you do it. And I end up with 13.56 grams left over. Okay, so let me walk you through it again. Students always have a difficult time with this, how much of the excess is left over. Go back to the limiting reactant. Move using your mole ratio, and that tells you how much you use. So that's what I got when I took the 0.0375 divided by 2. In moles, I used 0.0188 moles. I subtracted it from the original number of moles to get this. This is left over. And then I just converted it to grams. Okay, I think we have one more problem. All right, and in this one, I'm going to have you write the chemical reaction yourself. And there's quite a bit of that in the practice that we're going to do together. All right, so we have calcium hydroxide, which we just used, so that's a help. We just used that in the previous problem. So calcium hydroxide is reacting with nitric acid. It comes from nitrate. So there's my formula. Okay. Nitrate has a -1 charge. It's a double replacement. The hydrogen goes with the OH to make water. And I see that I have 2 OHs here, so I'm going to end up needing 2 of these, I know. I will make 2 waters. And all that comes together when I think about the charge for calcium combining with the charge for nitrate, which is -1. So I need 2 of those. Remember, you're thinking of this in isolation. Does not matter what the formulas were over there. And then that gives me my balanced chemical equation. So now I can write the information given in the problem. So how many milliliters of 0.35 molar calcium hydroxide are needed to neutralize 75 milliliters of 0.2 molar? Right? So here's my question. Here's this. The nitric acid is the one that I know the most about and can get moles out of. So get into moles. Do that by rewriting the big M, 0.2 moles per liter. Notice that I'm saving my volume because I'm going to be multiplying that by, don't put the 75 milliliters on the bottom of the 0.2. The 0.2 big M by itself means this. Now I will change the 75 milliliters to liters, 0.075 liters, and multiply to get my moles. 1.5 times 10 to the -2 moles. Okay. Take those number of moles, I'll write them right here, and move to the question using your coefficients. So times 1/2, 7.5 times 10 to the -3 moles. All right. Now, I know that this is confusing because you've got moles and you got a molar. So how do I get volume out of that? It's in here, okay? Volume is in the big M. Rewrite it this time, but flip it over because I want volume. And then my moles will cancel. So I'm going to take the moles I got and divide by the molarity. Now you can memorize that, but I think it's easier just to figure it out with the units instead of memorizing a bunch of pathways that you're going to forget when the test comes. So when you multiply these two things together, you end up with 2.14 times 10 to the -2 liters and then you multiply times 1,000 milliliters per liter. And you get 21.4 milliliters as your final answer. And that brings us to a short lecture 16 end, 40 minutes. Be sure that if you have time to go ahead and get started on the practice lecture, which is located under Exam 3 materials.